nitrogen truck coming in at least once a day to the site, and you will be wondering what is the truck doing and why are we bringing, we use our own refrigeration. What is it really helping us? And it's not a bad question to ask. And so I want to explain what are the advantages, disadvantages, and what the nitrogen does, and what it doesn't do, what's the benefit analysis of using nitrogen without using nitrogen. So basically the nitrogen pre-cooling is used in helium refrigeration, so we like to know advantages and drawbacks and explain various nitrogen pre-cooling. Although pre-cool, there are so many ways to use the nitrogen in pre-cooling. And simplified analysis is nitrogen is how does it compare to other options of using like the rest of the refrigeration if we don't use nitrogen. So the objective is to provide a rational viewpoint of using nitrogen pre-cooling, and how do we reduce the first cost of the components used in the nitrogen and the liquid nitrogen. How does the balance we get to? So LN2 pre-cooling, what does it do? In a steady state, basically if I take a 300 degree Kelvin helium gas and we want to make it 4 Kelvin of liquid in the door, liquid nitrogen helps to cool it from 300 Kelvin to 80 Kelvin, because 80 Kelvin is the nitrogen boiling temperature. Up to that, we can use nitrogen. And because the helium from 300 Kelvin to 80 Kelvin is around 1150, 1200 joules per gram, whereas nitrogen is 400. So we use around 3 grams per second of nitrogen for the energy balance on the first law basis, just to get the energy equivalence between what is giving the heat out to what is taking the heat in. And also, when we have this high pressure helium going to the cold box at 1820 bar, which is where the cold helium coming back after we use in the load at 1 bar, which is also, and there is a temperature difference we need for this heat transfer to happen. That's called the delta T, the heat exchanger process. That itself is a loss mechanism. So the bigger the heat exchangers, the delta T or the temperature to drive the heat exchange becomes smaller and smaller, and the losses become smaller and smaller. So what we're saying inversely is the size of the heat exchanger plays a big role on the temperature difference, which plays a role in the amount of losses that process creates. So the nitrogen also helps for the losses which we create in the temperature difference from 300 Kelvin to 80 Kelvin. So it contributes, one, to cool the warm helium gas from 300 to 80. Other is all the losses, the delta T losses coming from, because when you have the 1 atmosphere gas coming from 80K to 300, it doesn't come to the high temperature side. If the height is 300 is the inlet, this comes to say 290. So there is approximately say 10 degree delta T. That delta T has an enthalpy flux of the heat which has to be absorbed by some refrigeration mechanism. Either it can be liquid nitrogen or a turbine or something. So that's what it does. So it provides those two. And provides a refrigerant. And also the nitrogen plants, because they are commercial, large plants, big tonnage plants, they don't throw away the turbine output. So the turbine output is normally recovered in these nitrogen plants. The other thing is nitrogen plants also, because specific heat of nitrogen is 1.4 compared to 1.67 for helium, the heat of compression and the losses associated with it are less in a helium compression process compared to helium. So the nitrogen plants tend to be more efficient than helium plants for the same range. So because of these advantages, production of nitrogen is normally more efficient. So production of 80K up to 300K, 80K refrigeration is more efficient than doing with the helium to reach the temperature. So that advantage will be inbuilt if we buy nitrogen, because we are buying at a higher efficiency level. Also, now we are buying the refrigeration from 300 to 80K. That refrigeration capacity is available in the cold box, which otherwise the turbines would have been provided. So that way we can, the more valuable refrigeration. So okay, you have seen this before. So when we start at 300 Kelvin, watt per watt is so less or less than 1, and until we get to 80 Kelvin, it is like 3 watts per watt. So on this, is the exergic value or the thermal value of this heat removal from 300 Kelvin to 80 Kelvin is so little compared to going up this way, we are up to 4 Kelvin and 2 Kelvin. So using this as a pre-cooler is that much more advantageous. And if you look at this, say total energy removal 300 to 4K is 1570 joules per gram. And if it is 380 K, that's 1140 K, that's 73%. And the Carnot value of that 73% of the heat duty is only 13%. Whereas the Carnot work of going from 80 to 4K, the heat value is, the Carnot value or enthalpy value is 27%, but the Carnot work required to take it from 80 to 4K is 87%. So we are using we are able to get rid of a lot of less valuable heat with a much more with liquid nitrogen and with a less Carnot value area. So that's the main reason of why we use nitrogen is we're able to cover a lot of enthalpy range 380 Kelvin, which is 73% with a very small Carnot value. So what are the advantages? It reduces the capital cost, because you are buying the refrigeration directly without the compressors and all these associated equipment. And if you already have a machine, and that machine can, by providing liquid nitrogen, we can increase the capacity by up to 1.5 or more times depending upon what is a limiting component in that machine. So that means your capital, which you invested in the helium system, is able to produce twice as much by using nitrogen. And a smaller cold box, because you are buying the refrigeration from outside, which is, and although we need door, but we normally put it outside, so we don't need that bigger room. Provides a thermal anchor. This is another important thing. So if you have turbines and as the load varies, one of the problems varies, the temperatures move up and down. When we have these impurities we absorb in the charcoal beds at 80 Kelvin for air and at 20 Kelvin for hydrogen and neon and things like that, they tend to move with the temperature. But if you use nitrogen, that's anchored. So that temperature anchor point will make it, even if you have a shutdown of the refrigerator or something, not to propagate that impurities to go down into the lower temperatures, because any time if you have any upset conditions, it always go to a lower temperature level by cryo pumping. So the anchor point is very important. And it provides a stable operation, because now instead of 300 K reference, we have an anchor at 80 K. If we don't have a nitrogen, the temperatures can flow from a much wider 300 to 4K in a wider temperature span. Now they float between 80 K to 4K. So we are able to constrain the movement of the temperatures within the cold box and make the system and process more stable. Has a fewer rotating parts, because you bought the refrigeration instead of producing with the turbines, and keeps the load's temperature. When you are doing a turbine down or something, you can maintain your loads at 80 K using pre-cooling of the nitrogen. And impurities frozen in the warm heat, so it protects the other erosion and all. By any impurities coming in the helium gas, because they are frozen out in the heat exchanger, it won't hit the turbine blades. So the turbines will last longer once you have a nitrogen pre-cooling. And if you have starting with a load with a big solenoid or big magnet you are cooled down, 80% of the heat duty is cooling from 300 K to 80 K. 80 K to 4K is normally 15. At most is 20% load. So we use nitrogen pre-cooling to take advantage of the cool down capacity required, which is a low Carnot value cooling, which is easy to get rid of. So we use the nitrogen for pre-cooling. So what are the disadvantages then? Why don't we just use as a standard practice? So operating typically costs you more, because you have to truck it in, you have to maintain. Now, presence of different fluids. If the nitrogen leaks in, it can contaminate the helium and requires coordination of every day. Somebody has to sign these trucks, take the delivery. You got that nuisance factor you need to put up with. You got weather. Of course, we don't, it doesn't bother us as much as it used to bother, like Fermilab and all. Then they built their own nitrogen liquefier on site because of the weather dependency. We had only once after I came in 96 or 90s. At some point, because of the power, the nitrogen plants were asked to, they negotiate the power. If there is a peak power demand, they will be asked to shut down to get a much favorable rate for their electric bill. So at that time, they shut down our nitrogen. So we borrowed from NASA. So we were subjected to once in my 16 years here. And generally now we have to deal with ODH issues because nitrogen is, you can't differentiate from air if it is too much there, and you can get into safety issues. So these are the disadvantages. So also there are many ways we can provide this cooling. Although it looks like cooling 300 to 80 Kelvin, what is there? I mean, how many more ways? And some of the commonly used in industry is what we're going to talk. See, this is what we used to use in our small 1400s and all these machines, small machines we built as a vendor. And we used to take a slipstream of helium, high pressure going through the system here, and take a slipstream and use with liquid nitrogen and cool it, and this will go. And then we realized it, cooling 80K, and if we split it into two sections, the same heat exchanger, because the liquid nitrogen has half latent and half sensible, give or take. So the helium coming from 300K will cool to half to 184 and 184 to 80, but this side will stay at 80K. Gives a big temperature difference, or makes this heat exchanger much smaller than doing it this way by spreading that, not taking advantage of the cooling curves. So there are differences in how to take advantage of the fluid properties in designing these types. So then when you integrate the same thing, type 1 into 3-stream instead of 2-stream heat exchanger, you can inject that. This is typically how the ESR used to be until we modified to do not like this, type 5, but this is another one where you can use the boiler. This is out and take the high nitrogen vent through the same heat exchanger. And this is how we modified the ESR from this concept where we were directly injecting nitrogen. So we built in the boiler and we built this heat exchanger. So we made it so that there is a lot more efficient way of providing this cooling. And this is one of the types which is commercially used. This is how the Lindy designed for SMS pre-cooling on their main refrigerator. We'll come and talk about the differences in these. So types 1, 2, and 5 are commonly used in small ones. 3 through 6 are used in medium to large machines. And the temperature at 80K level, we normally design so that the enthalpy flux coming back from the cooling curves is small on the turbine. 80K and below, the refrigeration is provided by the turbines. So we need to keep the temperature difference below 80K as small as possible. But that's not basically driven by the front end, it's driven by the heat exchanger below the 80K. So a lot of people think if we make these nitrogen heat exchangers big, the temperature will reach at 80K. It is not true, so that I will point out. It is this enthalpy flux going from 80K down is controlled by the heat exchanger 80K, below 80K to 60K heat exchanger, not 80K to 300K heat exchanger. So people, if you, think about it, if you don't understand it, come back, I'll explain it. Some of the folks in our group can explain it. And so if you have any questions, if you don't understand it, can you stop me now, or we can go on later, but make sure you get those points. Well, each of these types, so let's look at, let's take an example, say 10 grams per second helium on the high side, and let's say we have a warm end delta T of 10 Kelvin and a cold end of 1.5 Kelvin, and let's compare how these things will. So if you put in type 1 through type 6, and break it down into the heat exchanger as given in those pictures, and you calculate the mean temperatures difference and Cmin. These are the heat exchanger vocabulary, is the thermal value of for a given mass flow rate, and this is the ratio of the Cmin to Cmax, and these will determine how balanced the heat exchanger and high side to low side. The closer to what this is, it becomes that much harder to design the heat exchanger. it becomes that much bigger in size because as this ratio is smaller and smaller, that means you got easy to change in one side fluid property. You will have one end of the delta T will open up as this ratio is smaller. So if you calculate UA, or the amount of surface area you need for each type, it will tell you how much you have to pay approximately based on the UA. NTUs will tell you how long this heat exchanger needs to be there to approach a given pinch point. So this NTUs will normally tell you the length of the heat exchanger you need, UA will tell you the cross section or the amount of surface area you need, and the effectiveness will tell you how effective you are able to approach it. So for a given conditions what we talked, when you compare it, this is how they compare. So normally type 1 requires almost twice as much surface area and twice as long, and you can see the advantages and how these various things will compare for each type of arrangement you use. So if you can, these three are the main drivers. If you look at this one in the figure, and if you look at these, they will tell you how big these heat exchangers are. Taken a smaller heat exchanger, and if you split it, how to take advantage of the cooling curves to accomplish the same process. So type 1, 2, 3, the heat exchanger effectiveness is really has to be very high for the conditions we assume to accomplish for comparative purpose. And sometimes it is very hard to get to that high effectiveness. Requires 60% more UA than type 5. So the heat exchanger size grows very, very fast if you happen to choose a wrong type of arrangement. So let's compare. Let's say, okay, we take this in a simplified way, like type 2 and a type 5, and say, okay, let's compare. How does so number one, ratio of let's say we have the same amount of surface area we're going to use, and let's say we have a slipstream going from the nitrogen heat exchanger has slipstream, the fluid going through this pass, varying from say 0 to 15%. If you use the same surface area in both the types, type 2 and type 5, our nitrogen consumption in type 5 will reduce as you for the same amount of area. Or, to put it the other way, if you fix the surface area, and the nitrogen usage will increase by like that between the two types. So these two types, you can see, although they look same, because of this delta T here, which is the loss mechanism, which is not there here, which is smaller, has such a strong influence on your amount of nitrogen use or surface area you need if you want to minimize the nitrogen. So one or the other, you have to give, either you have to pay for more nitrogen or you have to pay for the more heat exchanger by allowing this delta T to open. By closing it up like this, you are eliminating that losses. So those are the important parameters you need to understand how these loss mechanisms propagate through various. So if you take, say, the type 2, and what did we say? So we are saying we are putting nitrogen at type 1 where we inject it, and the helium is cooled from 300 to 80 K. So in the middle, it opens up to 180. If you look at it, see, this is the nitrogen, which is latent heat, constant temperature, and it starts warming up. This is the helium getting cold. If you plot this temperature difference between these two, which is driving the heat transfer, and if you use it at the middle, this is how much the temperature difference will open up. And so that's what the loss mechanisms are. So there are another issue with these various nitrogen-free cooling is when we use the type 3 when we injected nitrogen here and we have the helium, say for example we had a huge punch from a refrigerator from the magnet, and you have a lot of low side flow coming. So this temperature will drop very quickly, and that will happen is that will freeze the nitrogen. Because if it falls to say 20, 30 Kelvin here, which is not uncommon on a huge bunch, and this will freeze the nitrogen here. Nitrogen itself doesn't expand when it is thawed, but what happens is because they are layered, you have helium and you have nitrogen, you have helium and high pressure helium and low pressure helium. This the low temperature helium, which freezes, doesn't freeze equally because of the flow maldistributions. So when we start warming up, we have the danger we can warm up on the top end of some of the passes, and some get wound up in the middle and build up very high pressures, and both ends are still frozen. And we have heat exchanger failures a few times by the pressure build up in the middle, still both ends were frozen with the nitrogen. It happened at Oak Ridge, happened at I think CERN, and so this is not uncommon. So we go to the other. If you go to these other arrangements, that effect reduces, because actually if you go to this arrangement, it's the minimum of that effect, because we are using this this helium low temperature, which is very cold, is not going through this nitrogen pass, so it is well protected. So those are the important parameters you need to understand in designing these things. So type 6 arrangement, it was interesting because when I was writing it, we were going through the SNS commissioning. We had a lot of discussions with folks, Vendor Lindy, but they were convinced there's no difference between type 6 and the other, because I didn't have this analysis completely done by the time, and then when we built it, we figured out that's not exactly the same, because what happens is, we go back to see this is full of liquid nitrogen, and when it is driven by this heat, by the gravity, it normally the flow circulation through this is anywhere from 10 to 20 times more than it can all vaporize by mass. So this interface, when they control this, the amount of nitrogen they are putting by this temperature, it always moves here in this interface region. So it's very hard to control the liquid vapor interface here, which has a problem with the controlling this temperature here, and the whole refrigerator will lose heat, and it has an effect on your other rest of the process and your temperature stability. That's what happened for the NASA 3.5 kilowatt machines. That was one of the things contributed in not able to have a stable temperature control at the loads. So the other, and now when we go back to like splitting the helium into two stream heat exchangers, then we can see how the helium, based on the unbalance, there is a minimum of nitrogen consumption. It will reach, on either side it is more than the optimum. So, and to control the nitrogen, most of the time they use nitrogen vent temperature, which is, they think of the polarities, then we should control it. Actually, the nitrogen consumption is less sensitive to the nitrogen vent temperature than the temperature difference on the helium to helium heat exchanger. So basically, the helium to helium heat exchanger, the temperature difference is the one direct indication of how much nitrogen you use compared to the nitrogen vent temperature, because that's a huge shock and it's very hard to control, and it doesn't really reflect the minimum to control. So there are three features which are apparent by using a bypass control valve, then integrating that into the same heat exchanger. So you can control how much bypass you are using when they are all in the same one common heat exchanger. You don't have a way to control the amount of helium working against the nitrogen. And basically, to minimize the nitrogen usage, it's a strong dependencies on the helium-helium heat exchanger and not the helium-nitrogen heat exchanger. That's important, and very few recognize it. And if you look at it the other way, is so if you have this is the helium-helium heat exchanger delta T, and this is the amount of usage of nitrogen. This is the helium-nitrogen delta T, whether it's 5 Kelvin or 40 Kelvin helium to nitrogen. The influence is a lot smaller from the nitrogen heat exchanger compared to helium-helium heat exchanger. So basically the helium-helium heat exchanger has the strongest influence on the amount of nitrogen compared to that other one. This is on a same one on a different axis. So the pre-cooler, basically you want to size it, the heat exchanger, how you layer it, how we get into that, which is important in terms of the nozzle, headers, stacking. All these parameters play a role in the plate fill heat exchangers, and that what determines whether you have what is the effectiveness you reach and how well you are cooling. Because if one of the passes bypass, you won't reach the effectiveness. And you want to use the warm and helium to helium delta T as your guide in controlling the amount of nitrogen you use. Those are the main. So if you happen to have any of these types, what's the best way to control is another thing is in the book for you to use it. So, and if you have, say, if we design a system which is designed as a refrigerator, or if you, then you have to use as a liquefier, we know the duty from turbines to heat exchange changes a lot. So then we may want to change, that means not only the turbine flow is the medium pressure flow, the load flow is the low flow. Then you may need to balance the high side flow against these, and you may use different arrangements where you can shift it so that most of the refrigerators, if you see in the field, have this medium pressure coming back very cold or wasting the refrigeration because the stacking arrangement and they are not exchanging heat properly, or if you change the mode, it gets worse. So they all need to be thought through in the design phase, so you are making provisions in case this is what you anticipate. So if we want to compare the operating cost, so let's take, say, 1 gram per second of helium from 300 to 80 K is what we want to liquefy. Whether we do it with just the nitrogen pre-cooling, use 1 turbine or 2 turbines, and this is how it stacks up. So if in one case we have just the nitrogen, and if we use 1 turbine, it reduces your cost. If we pay nitrogen 6 cents a liter and electric power, this is a few years ago, 4 cents a kilowatt hour, and by using one, now I mean it will be 38% more efficient. Or if you use 2 turbines, it will cost only half to get the cooling with turbines than the nitrogen pre-cooling. But for the other advantages, what we talked about, we still use that. And these are my old numbers. Say for example, we use around 500,000 a year here. Say if we use type 1 or 1 turbine, we can reduce 30% of our nitrogen. If we use 2 turbines, half of it. But it's not that simple because that can only be integrated into the main helium refrigerator. But half of our nitrogen usage is the 2 Kelvin box to cool the electric motors at nitrogen to the nitrogen temperature. That cannot be integrated into this. So basically, unless it is planned from the beginning, it is not that easy to eliminate nitrogen once you start at the plant. Because people ask me, should we go back and change it to the thing? But the nitrogen usage has been well distributed all over. And for the amount of nitrogen we use on site, it still doesn't justify for us to have our own nitrogen plant here. Then the plant is too small to be efficient. So that's what that. So that's basically the nitrogen pre-cooling and why we have the everyday 1 or 2 trucks showing up on our site. Now we go to we use 2K operations on site, and similarly there are so many ways we can achieve 2 Kelvin, and we want to present some of the some of the options available to achieve 2K and the similar trade-offs like what we did with the various ways of doing it. Yes.
What type of pre-cooling are we using here, JLab? What type?
We are using like a type, say for example, I told you at ESR, we modified from type 2, yeah, and whereas at CHL we use type 5, I think. Yes, we use type 5 at CHL, and we went from type 1 to, no, type, at ESR we modified from, what did you say there?
You said type 1 to type 5.
Yeah. Yeah. So,
I don't remember what CHL is.
yeah, that's right. And we use type 3 at CDR. Yeah. No, sorry, not type 3. Type 4. We use type 4 at CDR. Okay. 2K is what we use quite a bit here. Of course, anything below 4 Kelvin, these processes are applicable because most of our folks use 2K. We wrote most of it to provide the comparison at 2K. See, below 2.17 or lambda point, the superfluid has a lot of advantages. That's why we use 2K in our SRF cavities because the heat transport is no more by boiling, it is by convection. So you do not have any disturbance from the heat transport phenomenon. The conduction of the 2K or the superfluid helium is so high, it is as high or better than the boiling heat transfer. So, and that is the reason why we go below 2.17 Kelvin. And as you go down as low as you keep lowering the temperature, your amount of heat flux you can put in before you change it to the boiling will increase exponentially. So that's why we always have this difference, no? People who want to operate, they say keep pumping down, but for us to keep taking down costs you two ways. One is it reduces the capacity available at the refrigerator. Other is because it increases the pressure ratio, the reliability and other things come down with it. So you are paying a price. So we try to balance as the in between at CHL is what exactly you need for the operating conditions and what is the price capacity balance and operating cost and the reliability. So that's what we do indirectly without bringing it to your attention. So, I mean, we could have run it lower pressures at a reduced capacity, increase the operating cost and less reliability. But if it's not doing any more good than what you can do at a higher temperature, that's why we operate around 2.07 to 2.08 in our Linux. So because some of the nuclear models have been designed with very high heat flux and they are limiting, so we will be at full job, we will be operating Linux at a lower pressure because of the very high heat factor in the cryo modules. So broke it down to 4 types which we normally use. And one is the vacuum pumping, sub-atmospheric refrigeration, cold compressors, and hybrid. These are the 4 broad classes. I mean, there are subdivisions in each one. So let's say this is the simplest one. This is most widely used in small magnets and small tests, and they carry this to the nth degree, and they forget what they are paying by not looking at this closely. So they have a refrigerator, or they buy this liquid from a door and they put it in and they pump on with the vacuum pump. And then we can add a small heat exchanger here going from 4 Kelvin to 2 Kelvin and do the same thing, and we can see what it does. Say 1 gram per second, let's say we are able to process through our vacuum pump system. So to liquefy on an ideal basis, including the recovery of the turbine output and an output basis, it costs you 6840 joules per gram to liquefy it. And this is what the vacuum pump will cost you to go to the 2 Kelvin. But when you flash 4.2 Kelvin liquid to 30 millibar, you only get 15 joules per gram because the rest 5 joules is enthalpy, because you're starting at 11 joules per gram enthalpy liquid at 1 atmosphere versus it's only 5 joules at 2 Kelvin. So you will only have 15 joules of delta H per gram per second. Or on an ideal basis, this is the 4K plant input power, this is the vacuum pump input power. This is ideal, and if you get only this much refrigerant. So you are costing 600 watts per watt on an ideal. Or in a plants of this size, give or take 8 to 10% is the carbon efficiency of these plants. So if you use that, that means we are putting 6 kilowatts per each watt we use at 2K. And that's pretty typical for CTF size systems. So if you use that heat exchanger we talked about, this heat exchanger, which is very small to integrate, and what it does is, because you are able to cool 4.2 Kelvin back to 2 Kelvin, it gives you 20 watts per watt, although the remaining will remain the same, the cost of producing 1 gram per second liquid and the vacuum pump, but your output or your heat input went up by 25%. So your useful, the power input per watt has dropped from 600 to 450. So that's a 25%. It's a very small investment, has a very big reward. And that's what I tell the people when they're pumping, when they use type 1, I say, at least, you're committing a crime in my mind because you're using 6 kilowatt per watt, but at least do a simple heat exchanger. At least you're improving 25% with a very small investment. So if you increase the size of the heat exchanger, how does this trade? Is after 3 to 4 NTUs, you already reached the max. So even a small heat exchanger has a very huge payback. Right? 2 to 3 NTUs is a very small heat exchanger. So the advantage of this system is simple and small capital cost, but operating costs will go through the roof. So don't use it for big loads. So other one is the subatmospheric systems where you take the 30 millibar coming back from the load 2 Kelvin, you try to recover as much refrigeration as possible. But if you want to recover more and more of the refrigeration, which is already 30 millibar, the pressure drop will play a big role in the heat exchanger. To exchange the heat, you need pressure drop. And pressure drop, as the pressure drop increases, your vacuum pump size and the pressure ratio, they both go up very exponentially. So now we are in the dilemma. What is the balance between these, and how do we balance pressure drop versus the heat exchanger size versus what's the efficiency? And that's where Pete did his work for his master's, and that he will be presenting that work in his course. And this comes in after 3 more classes. And where he will go into details of how these optimizations of vacuum pump work, refrigerant recovery work versus the 4K plant. So this was Sam Collins, that's Bob Johnson. This is where me and Dana used to work at CDI. This is a refrigerator built for Stanford in the '69. Was a 300 watt machine. This was one of the first ones started our SRF activity with a 300 watt machine at Stanford. I mean, most of the work dates back to this machine and Apple project or whatever they call. But that's where the roots of what we make our living today here. I mean, quite a bit of work was done there. So this is how, in a simplified way, it works is you have it 4K to 2K, and you try to recover that refrigeration from there to the vacuum pumps, and you use the high pressure flow to cool it and integrate into the refrigerator, some at room temperature, some at 10K. So you're absorbing, you're splitting the flow to provide this wasted refrigeration otherwise to cool this and inject it and improve the process. So this design is, so if we design well, you can probably change it. I know it's pushing the limit to say 0.1 gram. So let's say we are taking 1 gram per second here as our example. So you can push it as high as 0.1 gram here and 0.9 here. Of course, the heat exchanger will catch up with it, which is not realistic. But just as an idealistic comparison, I said, let's say if we do that, how does this compare to the other processes? So that's what we do here. So if you do that, the power, we started with 600 watt per watt with direct vacuum pumping, ideally. With one heat exchanger, we brought it down to 450 watt per watt. By doing this, we can bring it down to 300 watt per watt. I mean, you can see how fast we are making progression in reducing the total input power watt per watt by this simple one step at a time advancements. So, yeah, I mean, this is basically the trade-off between your pumping capacity as your pressure drop increases versus the refrigeration technology. So advantages, you can use an existing 4K plant, you can build a side card, and you can improve your 2K. And at CDF, where the 4K cold box core was designed to do this, but never been analyzed to this level where we never able to get to this level where we get only 3.5 kilowatts per watt level. The problem with this concept is there are a lot of subatmospheric vacuum pumping systems at the room temperature which are prone to contamination. And they are not efficient because your pressure ratios are high, and they're also not reliable. And the pressure drop in the low side is high, and adds into the problem itself. So the next is our CHL, all the way use the cold compressors. And so this is, of course, we started with 4, then we added the 5th at CHL, but at SNS, they still have the 4 for the 10 temperatures have the same pressure range. So this is our CHL and cold compressors. So this has many advantages. One is we don't have any warm and subatmospheric components. Everything at the room temperature is above atmospheric pressure. So it is very low susceptibility for contamination issues into the subatmospheric. And also this process is probably the most efficient compared to any other we know if the cold compressors are designed appropriately. The disadvantage of this is because these compressors are in series and the pressure ratio is too high, and establishing the pump down path took us quite a while initially. I mean, as I outlined at the beginning. And once we figured it out, now we are not as concerned as we used to be. So figuring out the pump down path itself is a science. So as we increase the pressure ratio, I mean, we are around 35 level presently, and it varies between 30 to 35 depending upon pressure ratios. And the efficiency of this train remains pretty constant, but the capacity comes down substantially as the pressure goes down. So during the initial commissioning, like I said, it took us many, many years to get there. And after we built the second 2K box, we saw a lot of these issues which were existed in the original, where the cold compressors were connected too close to each other without enough breathing place on the flow straightener. So the influence of one compressor on the next stage was very strong. So what we did when we built our 2K plant in the 98, 99 time frame, with the flow straighteners, we increased the volume in between. We did a lot of other things. And we got 10% more, another 500 watts of 2K for the same 4K plant. And that's where they said, JLab said, go back and rebuild the original, do the new design. And although, I mean, it was, when we were making the changes, we were not sure because we had made right from the theoretical basis and from all the practical experiences, we made the changes. And first time when it didn't start, I was very nervous because we made so many changes taking us a lot of directions. But when we get this going and recognize the stability and the capacity, I mean, then we were okay. But first few days, we were very nervous because when we reduce the pressure drop on the heat exchanger in the 4K to 2K, one thing we did not recognize is the influence of that pressure on the torque characteristic of the cold compressors. Now, by not having the pressure drop, the torque demand on the cold compressor one increased, and we have no knob to turn to cut that back. We have no valves to throttle it or anything. So basically, then we figured out what we have to change is the voltage versus the frequency characteristics of the cold compressors, and we figured out a way. And when we built the SNS, this was a new record. We never even thought we will fall into this trap where we built this just like JLab, and we put everything, we went, started, doesn't start, 3 days, and we're scratching our heads. And I said to Fabio, I said, if you think I know, I can't see anything wrong on the cold compressor side because I know the wheel, I'm involved in turbine designs, I built some of them. It's not coming from the turbine. I said, go get me a power analyzer. And when he brought a power analyzer and put it on the frequency down, right, we found a 60 hertz dependency on the power factor. Every 60 hertz, it reaches the power factor 1 and it drops and it has an oscillation. That's when, this is coming from the electronics in the frequency drive. It's nothing to do with we don't have, JLab frequency drives don't have these characteristics, at least not this significant. So what we did is, okay, now that we know the root cause, so let's find out the pump down path, like I was telling you before, so that no more than one compressor will be at the minimum power factor when we adjust the speed ratios between relative speed ratios. So when we worked out the algorithms between all the four, so that no one reaches the minimum at any given time, and figured out we had the successful pump down. So finding out what is the cause of the problem itself sometimes is very difficult. And until you know absolutely sure, that's when we were talking to early kid folks who designed the compressor, they said they would have never thought about looking at that side of the shaft. It would have never been dawned on them to think it's coming from that side. They would have been continuously looking on the compressor wheel only, because traditionally the surge comes from the compressor wheel designs. And because we are so sure, looking at the wheel shape and the pressure ratios where it is happening, and that's where we started looking elsewhere. So if you look at these on a thing, and this is how the power factor average was maintained. The minimum was like this, the maximum was like, so you can come up with the speed ratios where you don't hit these minimums at more than 1 at a time. And so these are all maybe. Then we were looking at how do we correct this power factor. We could not come up with one at that time. I don't know whether Fabio is still looking at gave up, but we could figure out without interfering with the electronics they supply how to correct this power factor. So basically, we are living with that path. We figured out where the gear ratios are such that they will not hit a low power factor on any one more than 1 at a given time. So how does this work? The comparison is if you use the same Karma analysis, you will get to 220 watts per watt on an ideal basis. And the advantages is it is the least possible contamination, high efficiency, pressure drop on low side will not affect because we are injecting back into the 1 atmosphere at the main cold box. This requires the compressor space because there is no subatmospheric room temperature compression. And basically, everything is 1 atmosphere or above and reduces the room size and displacements required. Disadvantage is very limited commercially available. The only people made is the early kit today. Nobody else took this to the room temperature level. Either Liddy or IHI or everybody only used partial and the rest they use warm compressors. And the increases well, because we are pumping the heat back into the 4K, we need a bigger 4K, of course. I mean, the 4K capacity, either you provide through the 4K cold box or through the refrigeration recovery, has to be provided somewhere. It's not going to go anywhere. So higher capital cost because there are not that many people producing this and not enough competition. Higher reduce, turn down is not as great as other options. And slow to reach the operating conditions because of this compared to other options. So hybrid systems where Torosopra was the one which was originally designed with two cold compressors and then the warm compressor way back, I think, before the CBAF. That was in the 80s. That was the point you use. That was the 15 grams per second before CBAF. And that's where they projected from there to the 250 grams, 235 grams per CBAF to all the way forward and didn't see through all the issues we faced later on. So when it comes to that, these are the use 2, might 3 sometimes, use that to raise this pressure to anywhere from 0.2 to 0.4 atmosphere. So the pressure drop influence is less and then you still have a subatmospheric. But you can approach the screw compressor level instead of the vacuum compressors now at that pressure level. And you can have various arrangements to get there. So, but it will give you the pump down easily because you can use this compressor to get it down to 0.2 atmospheres with this before you start these cold compressors. That makes it much easier to pump it down from there down. Another is because of this warm compressor gives you more turn down range. Biggest thing, what I thought at least is in the case of Weiss Sun is they have existing plants and they needed more capacity there. They would have gotten if they used all cold compressors. So they can use additional 4K capacity. They added more turbines and everything into this box by this. And so they got more 4K capacity, 4 total refrigeration capacity plus turn down. So that's why they went this route. So I think even MSU is looking at doing this way because of they want to start at around 40% level and eventually want to go to the 4. So there are pros and cons of doing it away. So as we look closely and when we did our turn down, actually JLab turn down is not as bad. We were able to turn it down to 150 to 2. We vary our flow at CHL from 150 to 250 up to 60% level. We may not be able to get to 40%. 60% is not although originally we thought we cannot reduce below 80%. But in practice, we have the test data where we turned it down to 150 times a second. So I think if we spend more time and some research by how to manipulate the cold compressor inlet warm temperature, I think we can improve that rangeability of all the cold compressor. But nobody is taking that direction of route to find out those things and going into these hybrid systems. In my opinion, I think compared to the disadvantage of the hybrid, I think people should really look at whether we can do everything in a cold compressor way and get the range. Even if we get 50%, that may be sufficient. 60 may be sufficient compared to other headaches of room temperature and subatmospheric components and other things coming up with that thing. So there will be, if you use the same cold compressor efficiency because of the heat exchanger losses and warm compressors, will not be as efficient as all the way cold compressors. So that's basically I don't think there is other processes compare. This is type 3 of cold compressor. To see type 1 is just vacuum pumping by the heat exchanger. So this is where these types are used with a 4K plant carbon efficiency typically. And this is what we think each one will provide for relative comparison if you put everything else on an even basis. So in CHL2, we want to get at least this up more close to 0.19 level carbon efficiency. That's what our goal is to bring from 6 megawatts down to 4 megawatts at CHL for the same cold compressor capacity or the net capacity. So summary. Nominal specific work and the efficiency of these various was what we compared. So you saw in the table how these compare for all these types. And so the 2K efficiency is very strongly depends on the 4K plant efficiency. If you go back and look at how we analyze type 1, type 2, if you look at the two factors, one is the 4K liquefaction, one is the vacuum pump. 4K liquefaction is at least twice as the vacuum pump. So you can see how strongly the 4K plant efficiency influences the overall 4K. And approximately overall specific carbon efficiency is, we basically compare these. So That's basically the various processes of how we can do the 2K processes, relative advantages, relative merits of each one, and of course there are variations in each one, but at least you can see on a broad brush basis before you choose a process which way you should be looking at for your application if you're starting from ground zero. So, any other questions so far? I don't know. There's a lot of material. I mean, but the book covers to some extent, like I said, and if you have questions, we'll be glad to sit down on a one-on-one basis. Go over. The next one is, what are the various components we use in the helium systems and their historical basis and their relativeness is what we thought is worthwhile for some of you folks. Not really do this every day and probably will. So your 4K plant typically has, you have the load. This is what we are there for to process this load at 2K or whatever. We have the distribution system. We have the network of transfer lines, distribution boxes, and things like that. We have say subatmospheric and 2K box. We have liquid nitrogen which supplies the 4K box and also to the 2K box. We have vacuum pumps to process the vacuum shell vacuums. And now we have helium storage. We have LN2 which feeds all these. We have purification. We have main compressors. We have warm gas. This is a typical stack up of a 2K plant. All the components which will go into the system. So if we start with it, and let's start with okay, compressor. Most of the systems we use are 2-stage, and we use a 3-stage when power cost was the most important for commercial liquefiers like city service. I think your legal playback. I remember it has a 3-stage compression process where operating cost was the primary. And compressor is the one, like I was telling you at the beginning, we have a 300K very close to coming back, and we put in a 300K gas back. From the enthalpy level, they're equal, but what we do is we take this high entropy gas, we compress it, we reject the heat into the cooling tower, and we reduce the entropy. By reducing the entropy, we increase the availability in the fluid, which becomes useful in the turbines and providing processing your load. Basically, if you look at energy level, there's very little difference here. They all have equivalent enthalpy level. But the availability level, that's what the availability flux is, what provides the useful refrigeration. So those compressors provide, like I said, the circulation of the flow from the load. It takes it and processes it and rejects all the entropy reduces the entropy and dumps that into the cooling tower. Compressors convert the mechanical energy into the availability, increasing availability. The available energy present in the gas source, that's the one goes to the heat exchanger. Also, that provides both for your heat exchanger, delta T's, heat leaks, pressure drops, and finally to the load. So the availability, what we supply, is created by these compressors. That's where we put in our electric power, and that's our major utility. Yeah, in the past, originally we started with recip compressors when we had small systems, 1400s, and they used to break all the time because the compressor, because specific heat is so high, they used to get so hot, and we used to inject so much more oil into it, and the oil used to kind of is not that easy on the recip valves, and so the availability used to be very poor and limited. That's when the screw compressors, like I was, it's all started with Sam Collins, where he said, in these systems, originally they used to be dry compressors. They were all afraid of putting any oil, any lubricant, so they were all, Sulzer used to build these dry lab compressors, and they used to have a lot of dust generation and everything. And I think every 6 months they used to tear down the whole compressor, rebuild it. It's a more experiment on helium, not on management system than your experiment. That's the way it used to be when I started in the business. I mean, we had very little time for the physics experiment. It's most of the time is to get this refrigerator going. And
How did you get to 6 months?
what's that? Oh, I mean, I don't know. That's what they used to claim in those 3,000 hours is what they used to say, you got to tear down the sun. And then we went into these recipes where we started injecting oil. That's when whether you put a drop or whether you put a bucket full, we still have to claim it because it doesn't matter. That's when we went into the screw compressors. CTI was where we started, introduced the screw compressor. Recips and screws, all these technologies were introduced there into the helium business. So we all worked with some initial concept stages of, and we still have those, where we started and where we are. We came somewhat, but not as fast as other disciplines progressed, like computers or anything. But we did come far enough. And in the screw compressors, now that's become basically the standard in the helium refrigeration industry because less vibration, less maintenance, and although the screw compressor guys will tell you every 30,000 hours you have to tear it down. A lot of our compressors are running around 75,000, 80,000 hours, so we figured out by letting them float to manage it more than doubling the life in between tear downs. And most of the compressors, CHL and ESR have, are in CDF have 70,000, 80,000 hours. And before we go and do those. So, and this is a typical screw compressor, the two lobes. And so this is a screw, I don't think is working normally, they're rotating. See, this is all the compression processes. This is a PV diagram. You take the 1 atmosphere, you absorb it and you start compressing, and you discharge at high pressure. And again, this PV diagram keeps repeating. So what happens is, unless the suction pressure and discharge pressure are matching to your suction condition and discharge condition, suction condition is normally matched. The discharge condition, you can have two different things. One is, you may be compressing here and you are opening your exhaust valve, and the rest of the compression has to happen in your discharge pipe because the screw hasn't compressed all the way here. Or you might not have opened your outlet port yet, and the compression might have gone over. So your over compression is real. And you never want to do this. You may want to, in case of you have a question about you can't reach this, you may always want to do some under compression because this will really expose your machine to unnecessary stress. And this is where a lot of failures happen. So when you adjust your machine tune up, make sure your built-in volume ratio is on this side, not on that side. And all these factors are, yes?
Do you have a buffer time?
What's that?
Do you have a buffer time to avoid situation number 3 happening?
It's not the, this is, you cannot solve with buffer because
Okay.
it is in the screw. See, you have a port where the exhaust port opens, it's called the final volume. You start with the initial suction volume and where it compresses to, in this screw, it starts at the suction volume where they are meshed and you have this many screws are open to your suction gas. But as it's compressing, depending upon where this outlet port is, how many screws you are opening or how length, the outlet volume is normally fixed. So for a given amount of gas, if the outlet is not matched, outlet volume, so you get a different pressure ratio. It's irrelevant of what you got outside the compressor. It is inside the compressor which determines where we are. It's inside before the outlet port is open from the screws. So buffer volumes don't help it. So if you normally given a process, they will tell you, okay, tell me what your cycle is and we'll size it for you. That's a screw pump. So they will say, okay, we'll give you for a given pressure ratio, what's your ideal built-in volume ratio where that exhaust need to open so that you have a peak efficiency. Then they say, okay, if you don't need the capacity, you can use the slide valve. This is linear, and use it. And even these are not optimistic. It doesn't work that way. These are all collected on freon or air and not on the helium. They are lot worse than these on the helium service. That's why we don't use any of these. Basically, we try to match a built-in volume ratio, which is ideal, and we'll go into that. And then we let the floating pressure determine so that the pressure ratio is always staying, and we don't have to really worry about these unnecessary details and headaches in a floating pressure. So this is basically we tested way back at SSC, a lot of compressors to establish what the driving factors are in pressure ratio versus volumetric and isothermal efficiency. And this is what we're installing now as ESR2. We'll have the same machine which we brought, we just put it in there. When eventually commissioned, we'll have the same characteristics of these, all these tests, what is done. We should be able to reproduce it on ESR2 because that's what we have in the long range plan. And this is the setup. Isothermal efficiency around pressure ratio 3, you get the peak efficiency, 3 to 3.5, and it goes to parts as you increase the pressure ratio. So when the people, like I was telling at the beginning, when they do these optimizations, even when I started at CTI, we used to have different groups. One doing the old box optimization, one doing the compressor optimization. We rarely used to meet or talk about until we used to think we are optimizing. We don't know what the hell we are optimizing, but we used to think that way. And because optimization cannot be done on a subsystem basis, it has to be done on an overall whole thing. So, and that way you are able to utilize now at CHL, because the way in which it's optimized is we have a pressure ratio 1 and the medium is around 2.5 to 3. So that fits well for the first stage. But second stage goes from 2.5 to 20, and which has an efficiency of around 45% instead of 55%. And that costs us a lot of input power because you are talking 10% loss in isothermal efficiency translates in the second stage, which are each one is a 20 to 50 horsepower compressors, motors on them, and the loss of 10 points is many kilowatts, like 500, another 400, 500 kilowatts, 400 kilowatts each. So it's not small amount. So when nowadays now, Howden is building, we can tailor ourselves the built-in volume ratio. So they built this screw compressor where it's not like olden days where CHL1 has fixed volume ratio. We can change them unless we replace the compressor. Now the replacement compressors have the adjustment of where this final volume is in our control now. So we can adjust the built-in volume ratio to fit our process more efficiently. So that's what we installed at SNS. So, but SNS, with the time we got and with the instrumentation, and we did some testing for varying the built-in volume ratio and the pressure ratios, and we measured the volumetric efficiency of first stage and second stage, and you can see the influence of the built-in volume ratio. This is one of the characteristics won't be available to us because none of these manufacturers, screw manufacturers, ever have this luxury of this test beds available to them. And so, and this information is, we're trying to generate it so that we all can benefit from it. So same thing, if you do the isothermal efficiency, this is the volumetric is basically is the capacity. It takes more compressors to produce the same amount of gas. Basically, that's what the volumetric efficiency is. If your volumetric efficiency is low, that means you need more compressors. But when it comes to isothermal, this is the power. This is your bill. You are paying for it every day, every power bill. So you want to have your efficiency as high as possible. So if you look at it on the first stage, yeah, we want to have pressure ratio in this range, and in the second stage you want to have, and that's how the CHL2 cycle was designed to keep the overall pressure ratios at the peak efficiencies where we were to adjust these volume ratios once we have them in place. So ideally, built-in volume ratio should match, but we know with so many variations in operating conditions, you have to fix one. You're not going to adjust every day. So you have to figure out what your operating condition is. You have to first map it out, and you have to adjust and leave it there. So having the highest yeah, it is better to under compress than over compress. I explained you that, because if you compress it, you are exposing to more problems. And we do not recommend slide valve control for capacity control. Floating pressure will do a beautiful job. So we use basically the floating pressure. For helium systems, pressure rate is too large to provide by single stage machine. Although small machines only use single stage. There are many arrangements like 2-stage or 3-stage compressions available. The multi-stage compression is not attained if the gas is not cooled. Say if you don't cool, say like my car, what they do is they have multi-stage compression. They compress in first stage, but they inject that back into the second stage, but they do not cool it back. If you don't get rid of the entropy generated at each stage, you won't take all the advantage going to the second stage as good as you could have. So then the volumetric and ISO are important parameters, and they depend on the pressure ratio and skid components. Basically, you can have a lot of pressure drop in your coil separators, aftercoolers, and the oil removal system. They all play a big role. And these are all very interesting in establishing the new standards in this for the job. Compressor system, oil pumps, and all. So oil is used, like I said, is to lubricate is one thing, but the amount of oil we use is many times more than what we need for lubrication. It's mainly used to provide cooling. The helium, because of the specific heat is so high, 1.67 for a gamma compared to 1.4 for A or 1.2 or 1.5 for 3R. Because of the high specific heat, we need a lot. Each pressure ratio generates so much high temperature. So we flood these things with oil to keep the discharge temperature low enough so that materials and seals won't get damaged. That's the main main purpose of oil in this group, oil flood screw compressors. Also, it prevents, provides a good seal on the rotor so that there's no blowback and improves the volumetric efficiency. And lubricate. And there are two ways. One is external pumps are used to provide all this oil, and or you can use the discharge pressure to circulate the cooling oil, and only use the pump to just use for your lubrication of bearings and the slide valve. So, yeah.
What kind of oil is it?
It's I mean, you can use two types are available now. One is LBX, where we start way back, the synthetic oil, PAOs. Yeah, and there's another type now.
Is that petroleum based?
No,
No.
PAO is synthetic. I mean, not. Yukon is synthetic based. The other one, PAO. Yeah, I don't think they are petroleum based either. I'm not really sure, but that's where all the new systems are moving towards that. But the problem is they're not compatible to each other. Wherever you start, you're stuck with it. So we weren't there enough to put half in one and half in the other. And so now it's too late for us to go backwards unless there got to be a big change. I hope people like MSU, MSU have the existing cyclotron. I don't know, small, and if they decouple it. Whereas NASA has all other type of oil. So. And the advantage of that was it does not require as much processing. It doesn't absorb moisture as much, and definitely more environmental friendly than Freon. So I don't know. I don't think we can switch back and spread this all over. Okay. Normally we reject heat in two places on a compressor. One in the helium aftercooler, other in the oil cooler. So normally oil cooler is the where most of the heat is rejected, varies between 70 to 90% depending upon mode of operation. And aftercooler gets rid of the rest. And we use double tube heat sheet design people are familiar with an ATM. So the leakage is there, water is leaking outside, not from water into the oil. So we do not want water to get into the oil. It will end up in the cold box and it will freeze. Any leaks happening anywhere, whether you have water leak or anything, it will plug the cold box. Now we have to trace back and say, where is it? It started at the compressor, or the brake cooler, or the turbine, because we use water to cool all these things. And everyone contributed on some system or other in some instance. So once the water leaks, you have a bigger problem on hand. So we take extra steps in designing these coolers so that the water leaks out, not into the oil, if there is a leak down. This is how, if it is a less than 250 horse, we normally go with 480. If it is above, we go with 4160. And because these screw compressors require a lot of starting torque, we don't bother using reduced voltage starters. We just go across the line and start it because of the high starting torque required for these. And also they should not be started in less than half an hour because the amount of starting torque is so high, it draws so much starting currenting into the windings, they won't cool down unless you wait. And people, if you keep pushing that button again and again, you will burn the water. Final oil removal. Well, if you don't remove the oil before it gets to the cold box will remove it. It's not coming back to the low side. It will plug. And there are so many of cold box out there which have oil. So we go through extra steps to make sure oil does not pass the compressor into the cold box. And we go through so many levels of coalescers, then through the charcoal bed, and we reduce PPB levels. And we design them with various velocity constraints so that, and length to diameter ratios, to flow distributions, flow entrainment, the flow in the chop. There's so much science involved to make sure to accomplish this level of cleanliness in the helium, because your cold box is your ultimate vacuum cleaner. It does not leave anything in it and will not come back. It will plug.
Well, I don't know if you still do this, I'm just curious, do you still pre-treat your Yukon oil?
Yes. Yeah, we have oil treatment.
And why do you have to do that?
Because when we get this oil, especially Yukon, has so much moist water in it. And not only that, it has lightens, we call, where low volatile vapor fluids in it. When we compress it to high temperatures, which happen with the helium, all those don't stay in there, they come back with that thing and may pass through our charcoal, it will pass through the coalescers and it will end up in the cold box. So we want to make sure that all the lightens and the moisture are gotten rid of.
Jefferson, you treat the other oil?
No, it does not require this kind of treatment. Well, you want to help us to get rid of and make a change? We have put the oil yet in the new compressors. We can use help. He's laughing. Hey, I have to put the pitch wherever I can. Okay. I mean, this is what we went through in the floating pressure challenge. Basically, the gas management is there. It's very important. And what happens is we set it up, we start it, and the gas valves, everything is tight. But as we operate, there are out of leaks. And when we size it, we only size it on the first day when everything is 100% tight. But as the things get old, they develop leaks, and you have to allow and you have to anticipate all these in your designs so that not any simple small thing is asking you to go for a maintenance. So you should be able to allow certain amount of all these things in your plans so that your interval between maintenance can be longer. Like we got say 5 years because so many things have been planned, how to address this in between. And that all comes from your awareness of all the components we are talking about, all the cycles, all the duties. And once you are aware, it's not that big a deal. The question is being aware of it and addressing it at the design phase. That's a critical thing. And so like we said, compressors compress, and all we do is these two normally shut off both bypass valves. And and we allow it to float like what we explained. But when we are commissioning a compressor, let's say this cold box is not there. We are putting say CHL 6 megawatts in, and we are running on the bypass. That means these two valves are taking 6 megawatts of power through them. Did anybody thought that way? These are able, because the enthalpy is the same. If we put 6 megawatt, they will melt and you will have iron flowing down. But we are only using the availability created by the 6 megawatt. That's what these are basically wasting it. It's not the total energy. Otherwise, if 6 megawatts, like I said, all these pipes would be molten iron on the floor. But what I'm trying to point out here is, these leaks can cause you, putting your 6 megawatts can disappear in front of you, not recognizing. So these are very bad. When you don't need it, they are not tightly shut, they are costing you on your pocketbook. So the importance is, it can cost you, by this is not running, your compressor is running, you are paying the electric bill. Where is it going? This is where it's going. So, but that awareness, being aware of that fact is very important. Well, this is our cold box you guys have seen, which houses the heat exchangers, expanders, exhausts, valves, instruments, things like that. And like I said, all these things are. So the heat exchangers. This is what cools the gas from 300K down. Help finite number of, I mean, basically when we cannot, the trade-off, like I said, each corner step improves it, but it costs you a lot more. So we balance with some filler material, heat exchanger in between. So, but we have to make this heat exchanger very effective so that the cost on your next corner step is not that high. So those are the things these heat exchangers do in between, and we have to be very careful how these are designed. And they should be oriented vertical, especially if it is below 40 Kelvin, because now your density gradient on the high side is catching up with you. Because your heat exchanger stack, if you put it horizontal, say 1 or 2 feet high, the density of this stack of fluid on the bottom, the column height acting on that is a high pressure at the bottom, gives you a higher flow through the lower stack than the high stack. So you have already imbalance right there. And when you are designing 98-99% effective heat exchangers, you will not get there even with that kind of factors. So if we are stuck with horizontal heat exchangers, then what we do is normally we put in called hard fence. We create pressure drop. And this is against what you want to do, but you have to create so that you will have a flow distribution. So it's like taking a medicine, because knowing we have this problem. And the NTUs tell you how long they need to be. So heliums, they normally have very high effective heat exchangers. Pressure drop is important. And longitudinal conduction. See, when you have 300K on one end, 80K, the metal conducts heat from 300K down through the aluminum layers, or the copper, which is conducting. So you have to account all that. And that will add you, when you account it, anywhere from 30 to 25, 30% of length before you know it. And if you didn't know it, you won't get the effectiveness you're thinking. Calculating on the paper is one thing, making sure that is able to account in the real components is another thing. And all these factors, if you don't account it, you won't get there what you're calculating in the paper. And external heat leaks from the 300K cold box, the components go from 320K, 40K, and 4K. All these heat leaks have to be addressed. Orientation, like we said. So these are some of the things, the ratios we use. Pressure drop in the nozzle, pressure drop in the header, pressure drop in the distributor, pressure drop in the core. How they need to be addressed so that your flow distribution through each layer, because there are 20, 30 layers which are exchanging heat. If one of them is not getting the flow and something else is getting more, you will never get to the effectiveness we are talking. So all these ratios are proven to be the ones which will provide that, but these have to be designed at the specification level, at the design level. So this is the 1400 type heat exchanger, and which is outer layer is 300K to 80K like that, and this is the 4K. This is the Sam Collins original concept, which we built quite a few of them. I think I got a lot more for people. I guess if you have time, another 15 minutes, otherwise we will have to go, I guess. I think I got another 15 minutes stuff.
You going?
Okay. So the in the heat exchanger time, fin tube is what this is the fin tube heat exchanger. And there's around 30 fins per inch is the density of these fins. And there's a nylon rope in between to seal the, here, if you can see this, that's so that the flow is going over the fins and not bypassing. And if you look at it, it is not a true counter flow because the flow on the high side is going round and round, whereas the low side is going through. So each one round is getting a different temperature. So this is not a true counter, it is pseudo counter flow. So you have to add the effectiveness. If you calculate on a true counter flow, you will not get there. You have to add another 30-40% more turns to get to that effectiveness. So, and how to design this is the book, what we used to do at CTI when we built these things. I put it out there for people, applications need for it. And this is a brazed aluminum heat exchangers which are typically used in all large machines. These are the stacks I'm talking about, layers. And these are the distributors. And this is the nozzle. This is where the flow gets distributed to various layers. So brazed aluminum heat exchangers are used in large systems. And you want to make sure they are constructed with where they are very leak tight so that you don't leak into the vacuum shower. And they provide you very large surface area for a given volume. And longitudinal effect, conduction should be addressed, otherwise because it's aluminum, 300K to 80K or whatever, it conducts pretty good. And you got to make sure you added extra length of the core to account for that. Layering, like I said, we call adiabatic layering. You provide, say, one high pressure stream with two low pressure streams because the volume flow for a given mass is a lot higher, and you layer this. And if you have multi-stream like three stream or 4 stream, then it gets more and more complicated. So we call the adiabatic layer. Every unit, we have so many of them to make sure they're thermally balanced between the layers. And if you have a nitrogen, it is repeated so often. And all those things have to be addressed very carefully before they are constructed. If you're not paying attention, what happens is all these people, although they're professional companies, and they have no people coming in. And the torch handoff normally doesn't happen as smoothly as we should, although the companies claim the long time their in-house capabilities. That's what sold. And the new guy coming may not even know these factors, but by you putting it to your requirements, at least he will go ask some senior guy in the company, hey, what does it mean? So if you don't call for it, they may not even know to ask for it. He may be just building it, what he's thinking, because he may not be aware of these factors. So we need to write specifications to make sure we are covering all these parameters in our thing so that the people are providing those things. Yeah, these are some of the things. If you look at it, it is, like I said, 73% of the duty is done by 1/3 of the heat exchanger in length. From 80 to 20K is another 1/3, 20 to 40. So give or take, that's how the lengths of these stacks vary. And expanders, we use various expanders. They provide the refrigeration. Now the efficiency of the expander is also a loss, so that's why the higher the efficiency, your recycle flow reduces. You need at least 2 expansion stages to go from 300 to 4K because of the specific heat effect below 20K. You cannot make liquid helium without 2 stages. By just pre-cooling with nitrogen, you can't get there. It's very important, given number of cold expanders. The higher the number of expanders, the total flow will reduce and your system will be more efficient. So this is a recipe expander. This is what's in the, we have quite a few at CTF, which does the 4K refrigeration and machine refrigerator, which is now presently owned by the POC. And this is probably more suitable for small machines. They have very good efficiency, and they have also, because we can change the speed, we can adjust the capacity more by adjusting the speed. And these are the turbo expanders. We have these turbines at JLab running from 90 or 20 years, and some of them are still original. They are running around the clock. We haven't taken them out, so these are very reliable. And so, there are two types. One is a static bearing, where you have always a high pressure gas supporting the bearings. Another, that's the air leakage style, and another is the dynamic gas bearing, where the process supports the bearings, and that's the linkage style. And oil bearing is also used, but nowadays we are moving away because the cost of the scale and all those do not justify, because the gas bearing turbine sizes have vastly increased. So there's a typical efficiencies. And 80K and 20K bed designs, what are the various things you need to be aware of in designing this? We normally use dual 80K beds, and we design for around 10 BPM, and we provided thermal stability. See, what happens is the valves, like I was saying, isolation valves on these beds, if you can't shut it down very tightly, if the flow is coming on your 80K side, you cannot regenerate them. And most of the plants out there, that is the problem. We just can't regenerate 80K beds, including our CHL. If those valves don't stay on, we can never get them warm enough. So to do that, you have to make sure the valve has a thermal loop, so that the valve itself is allowed to not to see one side 80K and one side 300K, by allowing it to stabilize it. And so that's why we specify all these into the specifications. That's how we were building. From the 80s, I'm involved in it. All these purifiers I was involved in. And the phase separator, load test, and these are all the parameters you should incorporate when you are designing these components into what is the velocities, so that the liquid is not entrained. Auxiliary port boxes include oil compressor boxes, which we went through, we can change some things like that. This is the SNS 2K box. Liquid helium makeup pumps. This used to be one of the very interesting piece of thing we used to have, and from SSC time, this is one I took myself on to get them shut down. Basically, we eliminated in most of the places by designing the process itself capable of providing that additional circulation. That's why when we're talking recently about the new design for Hall-D magnet, we told them we do not plan on providing pump set. We can provide that circulation. Including Brookhaven, when we did this update recently, we went and shut down their pump set also there. So, helium storage, and how do you size it, and warm storage versus liquid storage, and what does it cost, and these are all the factors are there. So this is a helium door at SNS, and we're putting some chemicals in air storage around there. And the advantages, disadvantage, and the cost comparisons of warm storage versus liquid storage. What are the various advantages and things. And the gas storage, basically, this is the gas tanks we use, right? This is because we buy gas in the gas form, and we're used to. We can maintain our gas inventory, say the liquid or gas, and we can do the process. But over the years, we are used to gas. We are dealing with it because that's how we're getting our gas. We built our operations around the gas, but it can be built around the liquid storage as well. You can have one large, one small, and we can still do the same things. This is the gas storage, various aspects of gas storage, and the distribution systems. This is one of the distribution boxes we built for Michigan State, which has a nitrogen drawer, a helium drawer. This is more like, this is I think 5 foot in diameter by, if I remember around, 10, 12 foot long. And this is probably the size of the distribution we need for the Hall-D magnet. And this is one of the, and of course Hall-D magnet also, that box will require nitrogen shield in addition to this. And that's a big undertaking for people who haven't done before. It will be an underestimate for them. They need to really pay attention to what's all involved in designing this type of boxes. These are the transfer lines. Dave is a good expert on it. If you guys have questions, refer to Dave. We inherited from him, so. And the nitrogen systems are, like I said, why we use nitrogen and how do we size it basically. This is our auxiliary systems. There's not that much theoretical stuff involved and more of the practices involved. So they are self-explanatory. And the gas nitrogen, where we use it and how we generate it. And purifier, this is another thing. Matt is going to give one class. Like I said, small line. Pete is going to give them the small 2K. Matt will go over. I will keep telling him that he made a mistake of letting him get his degree before he commissioned it, and he's dragging his feet. And that says purifier. And I'm hoping he's going to present data when he talks about it. And instrument A is one of the things we need, and this is another thing, how do we size it and what are the practices? And the utilities, electric power. And this is one of the things, I don't know whether Jonathan in the next class, whether he's going to talk about it or not, but that's, how do you get your feeds, how do you back up the power, because if the electric power goes down, and especially where we cannot put thermal cycles, such becomes that much more difficult. Cooling water. And this is where we reject all our heat. And we don't pay a lot of attention because there's so many cooling towers. And the reliability of the cryolysis system mostly traces back to these three factors: cooling water, instrument air, and electric utility. And very strongly to cooling water. My analogy to cooling water is we can have a beautiful horse. If the horseshoe is not at, it can only run as good as the horseshoe. If the shoe is not good, it's not going to run. So that's what it is.
There. Thanks, Ralph. Questions? Yeah.
What's that? See, when we have a sudden change in pressure or temperature, because they are operating on a constant thing, they cannot adjust. The flow changes very quickly through the heat exchanger we have between 4K to 2K. Let me go back to. Can we turn on the subatmospheric systems and go to the cold compressor, the subatmospheric, and let's go to. Okay. No, chapter 7. Basically, go back and load the thing and yeah.
Why don't we need hot plate?
No, yeah, it doesn't have hot plate anymore, so go back and go to chapter 7. Yeah. Yeah. So, okay, what happens is, this is a thermal link. We are supplying 4K from the CH model, and we are taking your 2K from the various loads. If we adjust, there are 40 JTs give or take between FEOL and Linux, and they're all working in sync, so which is providing a certain amount of load here. And then you have, it's not always constant, you have a variation. One JT may be opening, one may be closing. And so there is so much gas on it. For a given temperature here and a given speed ratio we set, it is absorbing, it is processing so much flow. All of a sudden, if you say, for example, you are bringing one warm from 4K to 2K, a warm cryo module we call pump down. and we are trying to bring that online. So we are trying to process the pressure from 1 atmosphere down. What we are doing in the process is we are increasing the flow through this here higher, although we are not supplying any more higher because it's already full of liquid. We want to get the pressure down. We have an unbalance here. So this temperature will keep dropping because there's more refrigeration than the high side to cool it. So it will start processing more. If it is too hot a gas, for example, after trip or anything, our return flows from various transfer lines increase, and if the heart is coming too hot, it will reduce in flow. So the flow change, which is very strong function of this temperature, so this is normally running around, say, 3.5 Kelvin. It can go as high as 4.5 or 3.2. And it's proportional, the flow change for a given speed. And any sudden change in this temperature is the one causes the trap. So all the processes, it can be up down of another linear, another cram module, some JT not acting right, or the controls froze up. That's most of the time starts here. The other thing happens is the controls. Something said, I'm not happy. Some card shuts it down. And these are some of it, I'm sure, what causes the trouble. But most of it from the process point of view is unbalance between these two process variations.
Anybody else? Question?
In your motors, the big motors, you had problems starting, and then earlier on you had problems with the power factor and the variable speed.
They're not big, they're small, cold compressor motors. They're only like 25 horse, 30 horse motors.
Okay, but
Yeah.
they're not DC motors.
No, they're variable frequency.
The variable frequency
Right.
DC motor.
No, frequency varies. By frequency means AC. Because we vary the frequency to that to change the speed of the compressor. They're AC motors. They're not that big. They drive the cold compressors. They are not like warm compressor motors.
On that note, what type of drive are you using?
What do you mean?
What type of drives, what brand or?
Hey, Jonathan, are you around? No, he's right there. I don't. Hey, Janet,
Yeah.
can you
I'll
help?
talk about the variable frequency
Yes, sir.
converter itself.
Yes, VFDs. It's okay.
Yeah, I can't remember offhand the manufacturer. We have two different manufacturers.
That's what I was wondering too, is would a different drive technology, like a vector drive or something like that, eliminate probably your susceptibility of power factor and frequency?
Yeah,
That's what I was saying.
see, they looked at it with SNS because we didn't run into that at JLab. That problem showed up at SNS. And when we tried to look into how to correct that power factor, we weren't successful because we found a path without it. I don't think they bothered to really solve it. But that's one of the interesting things to figure
I
out.
was wondering because a buddy of mine who's mechanical, he was my electronics electrical counterpart, did the same thing with our regular high power compressors for pneumatic systems. And granted, at least the scale what we have here, but each one of those was like 600 horsepower, and it was very significant.
Yeah, these are very small. These are like I said, 25, 30 horse. They are no bigger than that. So anyhow, yeah.
The biggest difference we have between SNS and ours is that
High frequency.
both the motors of both projects are the same.
Yeah.
And what that meant is that the motors for
Half
SNS,
it.
for the same stages, were oversized for the application. The SNS flow rate is half ours. And so we're talking about power factors and effectors of power factors on motors when the motors are lightly loaded. And the
Yeah,
power
but
factors are
no, that's not where our problem was. Then that's what we thought, but the other problem is why 60 hertz dependency. See, at 60 hertz it was dropping so low. I mean, that's a different problem than not having a good power factor overall. I mean, because the motor is too big, we understand. I mean, we can rationalize that because twice the size of overall is poor. But 60 hertz, we can figure that out. Why 60 hertz dependency?
Anybody else?
One more quick question.
Yeah.
How do you avoid helium contamination after you pass through your screw compressor from oxygen?
No, all our systems are positive pressure. The leak is out, not in. We do not have any systems sub-atmospheric above now. So air cannot leak in.
Okay. You mentioned your oil using, there may be water in there.
Oh no, I mean, like we said, the cold box will clean it up. Whatever is coming back from the cold box is completely clean. Anything left is frozen in the box. At 4 Kelvin or 2 Kelvin, we have nothing except helium left.
We would take out the moisture and the light end hydrocarbons, the light ends, prior to putting the oil into the compressor.
Oh.
So what Raul is pointing out is if you did have that moisture in the oil, it would end up in the cold box.
Yeah.
But in reality, we process the oil to remove those contaminants before we put it in.
Okay.
One more?
How do you maintain your cooling water temperature, cooling towers?
We have the cooling towers which have the fans which vary in speed, and basically the cooling tower, I mean that's where it varies. It varies winter to summer by I think 10 to 15 and but we can that doesn't really affect. See, we are working from 300 Kelvin scale to 2 Kelvin scale, where this change is less than 2 to 3%, and really does not influence except the compressor and so if we run out there, start on the fan, and so that's how they balance it.
Anybody else? Okay. Raul, I'm going to go out on a limb here.
Yeah?
You blew through a whole bunch of this stuff on hardware.
And what?
On the hardware,
Yeah.
the components.
I know.
And so often we engineers, that's what is exciting. So if anybody out there has, you want to see some more on a certain part of the system, let us know. Maybe we
Yeah.
spend a few minutes at
Yeah.
the next
I can do that.
session on it.
Right.
So just let us know. I think there's probably an email address on the website. If not, just come see me. You know, you can
Yeah.
get others.
Are you making an offer that we can go down there and tinker a little bit?
Only if we're running B.
This is right. You know it does. We might let you. But anyway, if you want to hear a little bit more about a certain system, let us know.
Yeah.
And maybe
Any
set some
particular-
time on the next go around because you went through that really fast.
I know. Any particular area of interest, I mean, any particular one, we can go on. We can sit one-on-one. A lot of guys in the group, and it doesn't have to be me. I mean, you get hold of, they can help you out. But I mean, anybody, if you have questions, feel free. We enjoy doing this. Make sure you do the right thing.
Let's thank Raul again.